Want to say hi to them. They have seen you on. They have seen your video. Anyway, we can. You any closing ceremony you are here? No. I'm closing. Saturday. But anyway, you say hi. I'll do it. पीछे कुछ तो चल रहा है. Okay. So I guess people rested yesterday and are fresh for today. Morning, you already have 2 talks on, I guess, quantum information and application. Right? Okay. So welcome to this special lecture of today. Before we start the lecture, maybe you remember that face that came on video on the first day. So this is Professor Arnab Bhattacharya. He is the Center Director of HBCSC. And maybe you want to say hi.
Hi! Wake up!
Okay. So today, as we know, we have this special lecture which we have named in the honor of Professor Rohini Godbole. So it's kind of a bittersweet thing for me because both Rohini Godbole, in whose honor this talk is, and Professor Shivapati Goswami, who is giving the talk, are both my collaborators for a long time. And Professor Rohini Godbole, about whom I will tell you more in a while, has been one of the foremost, most well-known high-energy physicists in the country, who worked for almost 50 years, who just passed away a few months ago. She was, apart from being a famous high-energy physicist who wrote almost 350 publications on various parts, she also was a good mentor to high-energy physicists. In fact, I can say that Vandana ma'am, Shivapati ma'am, and myself have been at the receiving end of sort of her advice and so on. So let me just tell you a few things about Rohini, because it is good to know about what the journey of somebody who started in a very humble beginning can be. So let me tell you something about her. Okay? So Rohini was born in Pune in 1952, and her early education was in the Huzurpaga school in Pune, if people have heard about this. Then she went to University of Pune. For her master's, she came to IIT Bombay and did her 2-year master's. After that, she left India in 1974 for her doctoral studies in the University of Stony Brook in the USA. She received her PhD in 1979, and she worked with Professor Jack Smith, who is one of the originators of the theory of strong interactions, which is quantum chromodynamics. Okay. After that, she came back. She was a postdoc in TIFR. After that, she became a faculty member at the University of Mumbai, where she was for many years. After that, she shifted to Bangalore. In Institute of Science, Bangalore, there's a Center for High Energy Physics, and she worked with that center till the last moments. So Professor Godbole, she worked on a large array of topics in high energy physics. One of her very interesting works actually was trying to figure out what would be signatures of the so-called top quark, which is one of the elements of the Standard Model, and what can be seen in a data detector in order to make sure that we observe the top quark. She also worked on the theories of supersymmetry. And another important thing that she worked on was saying that the photon, that to us looks like a massless particle, in the presence of quantum field fluctuations around, because we talked about it, actually doesn't remain a massless particle like a photon, but can have interactions now that a simple photon would not have. Okay, so this is the so-called structure functions of photon, because now it starts working like a particle with a finite size and not a point particle. She has a very famous textbook, which is called Theory and Phenomenology of Particles, which was published in 2004. Rohini represented India in many, many international fora. She was a member of the IUPAP, which you might have heard. So IUPAP has a high energy physics section. She was a member of that. She was on the Scientific Council of the Indo-French Center for Promotion of Advanced Research. She was on the Scientific Advisory Committee to the Cabinet of India. It's called SAC Committee. And she was on the DAE-DST Coordination Committee for the cooperation between CERN and India. And that is why we have experiments at CERN where our Indian scientists now work. And she started many of the summer schools. She was involved in starting the so-called ACRC school in the theoretical high energy physics, and also in the so-called in the Asia Europe Pacific School for High Energy Physics. So she was an enthusiastic teacher. She also was a tireless crusader for encouraging women to seek careers in STEM subjects. She has been a very visible person promoting this. She actually wrote a book called Lilavati's Daughters, in which she has written the life stories of many women scientists who are quite inspiring. Shivavati is definitely there. Vandana should have been there, but Rohini passed away recently, so we missed that. She also wrote a book called The Girl's Guide to a Life in Science. So perhaps you could have a look at that. It's quite interesting. She has been honored by many honors. She was one of the first few members of the women members of Indian Academy of Sciences and Indian National Science Academy. She has received the Padma Shri from the government of India, and she also has received the Ordre du Mérite of France, because she also was instrumental in Indo-French collaborations in many of the scientific topics. So I don't know why this is going ahead and then stopping, but I will try to make it stop. Yeah, these are some of her pictures, and if I could figure out how to stop this, I could simply stop. Let me exit this and show this to you. Okay. And in fact, the Prime Minister, this is a picture of her receiving the Padma Shri, and Prime Minister had even tweeted when she passed away about her and her work. So hers has been a very inspiring life, and we thought that it would be a good time to introduce you all to such inspiration. So yeah, so she unfortunately passed away just last year, and yeah, we lost a mentor and a colleague in high energy physics. So let us now go to today's talk. So today's talk is given by Professor Shivavati Goswami. She is a senior professor at the Physical Research Laboratory, PRL, in Ahmedabad. She did her PhD from University of Kolkata, after which, if I'm correct, she was a postdoc in first PRL, then in SINP, the Science Institute of Nuclear Physics, and then she was a faculty member in HRI, Harishchandra Research Institute in Allahabad, for a very long time. And then she shifted back to the PRL, where she is now. She has done very interesting work. Some of the interesting work also has been with me. But one of the important things that she has done is the following. So she will talk about neutrinos in this talk. And she will, of course, mention to you about the solar neutrino problem, which puzzled people for almost 50 years. The solution was found only in the beginning of this century, okay? So that is a time when we can really say that now we know why the sun shines, okay? The sun has been shining for billions of years, but it's only about 10 years ago that we learned it. So it involved neutrinos and their properties and measuring of them. And she was among the first group who figured out exactly what those measurements were in the first few years of this century. Later on, she has also been as a Humboldt Fellow in Munich and in Chicago as a Fulbright Fellow. She is members of all science academies that you can think of, but I will not go into that. She is a very interesting speaker, and now I invite her to come and talk to you about how to chase the neutrinos. So, please.
Thank you, Amol, for the kind introduction. And hello, everyone. And it's really an honor for me. And I am honored and I am equally sad to give this lecture, which is organized by, in honor of Rohini. It's very good that, this is organized, especially this is a school for Vigyan Vidushi, where, we should, of course, that's very nice, but I'm really sad that we are having to organize this. I first met Rohini when I was a PhD student, and Rohini tells this story with pride that my supervisor took me to her and told that, Subhabhuti, I want you to meet her. And of course, she was a role model, and in front, and at that time there were really very few women who were doing particle physics research. And so it was really, very inspiring to have Rohini in front of us, and and to get inspired by the kind of things she was doing, the kind of force that she was. And later on, because of Rohini's, because I was also interested in understanding why the representation of women in science, especially physics, is so less, and what can we do about it. And in this, I, Vandana, and all of us, even Amol, shared some common interest with Rohini. And then my interactions with Rohini became much more, and later, you become friends, right? Like we start from a role model, but then you become friends. And, so I really miss her, and I think all of us, we really miss her, but we have to continue her legacy on. So then with this, I will come to the talk, and I want to thank Anesh, Amol, and Vandana for inviting me to give this talk and giving a chance to interact with all of you. So I am from Physical Research Laboratory, which is in Ahmedabad, and this is also, this is under Department of Space. So one of the main thrust is space science research. This has campuses in Ahmedabad, and there is a solar observatory in Udaipur, and then there is also some telescopes at Mount Abu. So there are campuses in these three places, and there are research going on apart from space science in astrophysics and astronomy, atmospheric science, geoscience, then theoretical physics, and in the theoretical physics, apart from neutrino physics, we have quantum chromodynamics, flavor physics, collider physics, etc. So that's about PRL, and then let us come to the topic of this talk. So Bandana was told me that, give an interesting title, and I was trying to think that what can be a catchy title for this talk, and then suddenly I remembered this film. I don't know if you have seen it, Catch Me If You Can, and this was about some person who was I think some kind of a con man, some thief, and how he went towards the police side. So there was a kind of a confusion of the identity, which somehow, as the talk will go, you will see that neutrinos also are a little bit confused about their identity. So I thought it's catchy and it's sort of interesting. So that's how I got into this title. So let me come to put things into perspective and see that what neutrinos are. So I will start from very basic, that how do we see things, and we see things because light is reflected into our eyes, but we also know that light is not white. We know about dispersion, and we know rainbows formed, so we know that light has different wavelengths, and world is just not what we see by visible light. There is a full electromagnetic spectrum starting from gamma ray to the radio waves and infrared, microwave. Visible is here, through which we can see the world, and we can see at different scales, from very large scales to very small scales, and there are visible light is what we see through our eyes, but in these wavelengths we need special apparatus which are called telescopes. Now the first telescope was invented about 400 years ago by spectacle makers, Dutch spectacle makers Lippershey, Metius and Janssen, and this was greatly improved by Galileo Galilei, and these are some of the moon drawings which was shown through Galileo's telescope. And we have bigger and better telescopes now. Optical telescope, this is at NICE Observatory. These are some random examples. Chandra X-ray Observatory, NASA, Spitzer in NASA, CGRO, Space Observatory. GMRT you have gone and seen. So that's, that is a radio telescope, giant meter wave radio telescope. So there are, as times progress, we have bigger and better telescopes, and this is, for instance, the image of an exploding star through different light. So this is like a radio wave. So what kind of structure you can see? So this is like infrared, and this is the visible light through the Hubble Space Telescope. This is ultraviolet, then low energy X-ray. So a different star. So this is a Crab Nebula, which is an exploding star, and you can see the different pictures of different kind of structures through different wavelengths. That's why it's important to observe the same thing at different wavelengths. But light or the electromagnetic wave, that they are not the only messenger. Messenger is some bearer of news or information. Earlier days we know that pigeons used to be used. Now we are very much familiar with Facebook Messenger, WhatsApp, etc. So neutrino is an important messenger, and this is an elementary particle. It travels with the same speed as light, and it can carry information from distant stars. Now how do we know about them? Neutrino was born in 1930, and the father of the neutrino is Wolfgang Pauli. And Enrico Fermi gave the name neutrino. So why Pauli proposed the neutrino? The reason is radioactive decay. You know that there are three types of radioactive decay: alpha, beta and gamma. And a problem was observed in beta decay. So in beta decay, that time it was known that a nucleus will go to a daughter nucleus, in which a neutron will get converted to a proton and an electron. So it was known to be a two-body process. However, what one observed was a continuous energy spectrum for the electron. But if it is a two-body process, then electron should have a fixed energy which will be given by the difference between these two. But electron was having a continuous energy spectrum. So then people thought that okay, maybe the energy conservation is not obeyed in the at nuclear for nuclear decays, but Pauli didn't like it. So Pauli said that maybe there is a third particle which will carry the energy. However, because this particle was not seen, and we have to also satisfy all kinds of conservation law. For instance, neutron is neutral. It is going to one neutron is going to a proton, but there is an electron to conserve the charge. So neutrino should be neutral. It will not have any electric charge, and it should have a very either massless or very small mass. So this kind of, and it is also a spin half. So different conservation laws suggested some properties for the neutrinos. So once we add the neutrino, then this becomes a three-body process, and then the electron can have any energy because the energy is shared between the electron and the neutrino. So as I said that the properties were massless, chargeless, and neutrinos are also very weak interacting. By that time it was known that this beta decay is proceeding through weak interaction. So all these properties makes it very difficult to detect them, because usually if the particle has a charge, then it can leave a track, these kind of things, and it is very weakly interacting. So it was called the ghost particle. But it was detected in 1956, almost 25 years after it was postulated by the scientists Rhines and Cowan. And Rhines got Nobel Prize for detecting the neutrino, which is the electron type neutrino. I will come to it. And but Clyde Cowan had already passed away, and Nobel Prize is not given posthumously. So what they used was, they used a nuclear reactor, and they used the neutrinos coming from the nuclear reactor to detect the neutrinos. And the Nobel lecture by Rhines is called From Poltergeist to Particles. So like it was earlier not a reality. So we can conjecture many things, but whether it is a reality or not, that will come from the experimental verification. So only when the neutrinos were discovered, then it became a particle. That's why the Nobel lecture was titled From Poltergeist to Particle. So there is an interesting story. They were involved actually in the atomic bomb project. And they thought that, to let us put it to some good use, and they wanted to produce a neutrino from the atom bomb. But then they thought that that is not a controlled experiment which can be repeated many times. So for an experiment we also have to see, because we have to verify the results. And that's why they later on decided to use a nuclear reactor, and the neutrinos coming from the nuclear reactor. So now we know that there are three types of neutrinos. The Pauli's neutrino is the electron neutrino, and the muon neutrino, another type, and the tau neutrino. These are so called because they are emitted. There are also their charged lepton counterparts like electron, muon, and tau. So that's how they are so named. So this is like three flavors of ice cream, but of course we cannot test them. So there are plenty of neutrinos all around us. As Amol said, it's coming from the sun. It can come from cosmic rays, from the radioactivity inside in the earth. So that's called geoneutrinos. And so even the banana that we eat can emit neutrinos, and from the potassium, and so about 65 million neutrinos pass through the thumbnail every second. So in this room there are many neutrinos, and so each year, each month, I thought that this Harry Belafonte song is a good thing to describe, that plenty of neutrinos pass our way. I stand at my window to catch its eye, but I can never feel it as it passes by. That is because it is really very weakly interacting. But it comes from free. So the thing is that, from many natural sources it can come for free, so whether we can put it to some good use or not. So the main reason is we cannot see is that because they interact very weakly, and for instance to stop a neutrino one needs lead shielding 100 light years thick. So 100 light years is the distance light travels in 100 years, but for instance for X-rays this is 0.24 millimeter. So this is like the invisible particle, and one needs some kind of a special arrangement to, if you have seen Mr. India, you know that there is a special arrangement in which he could be seen, but here that special arrangements are called the neutrino detector. So, but because it is very interacting, weakly interacting, then we have very little interaction. So if we have a very big detector, for human body there may be one interaction per 100 years. So that's why one has to have very big detectors first of all. Then one has to go deep underground, so that because it's a very weak signal, we should not confuse something else as the neutrino signal. And then one needs a large statistic, so one has to observe these neutrinos over a large period of time. So this is the Super Kamiokande detector in Japan, which is the world's largest underground neutrino detector, and it uses 50 kilotons of water. And you can see this is also in a mine in Japan, and it is operating since 1996. And this is the kind of, the Super Kamiokande scientists fixing the photomultiplier tubes, which are the active detector elements. So the neutrinos produce charged particles which produce light, and the photomultiplier tubes are triggered to give the event. And with such a big volume, they observe about 30 neutrinos per day. Then the question is that, why should we try to catch them? If it is, such large arrangements, such costly arrangements are necessary. First of all, as I said, they are everywhere, and there are many natural sources like the sun, the cosmic rays in the atmosphere. So they can carry information from stars. Because they are very weakly interacting, they can come from the sun's, for instance, straight, whereas a photon will be interacting, so it will be trapped and it will go in a zigzag path. And another thing is that they pose interesting puzzles, and we like to solve puzzles. So we mentioned that neutrinos are coming from the sun. So we know that sun gives heat and light, but the same reaction also produces the neutrinos, and neutrinos come before light, as I mentioned, and they can also come in the night. Now the question which Hans Bethe and John Bacall asked was that, can neutrinos be used to study sun? So Hans Bethe proposed to study sun through solar neutrinos, and then John Bacall had a model, standard solar model, in which he gave lot of input about neutrino propagation in the sun and about the sun's properties, and computed the number of neutrinos coming from the sun. So what Bethe said was that, supposing we can detect these neutrinos, and we can calculate that if these numbers matches with the numbers that Bacall has calculated. So this first detection was in the Homestake mine in USA. This was an experiment by Ray Davis, and what he used was, so this is a neutrino capture on chlorine giving argon, and this chlorine was used in terms of cleaning fluid. So he used 600 tons of cleaning fluid which has chlorine. So the experiment was done in the following way, that you put this tank full of this cleaning fluid and expose it to the sun. So the neutrinos will interact with the chlorine and produce the argon. Then these argons were chemically extracted, and then they were counted by the radioactive decay of argon in the lab. So this was called the radiochemical experiment. And this exposure will be like, say, for a number of days, which is less than the half-life of the 37 argon to decay, because if it decays, then we cannot extract it. So this was not really a real-time experiment, in the sense that we were not detecting a neutrino in the real time, but we were exposing it, and from the number of argons, they were trying to calculate that how many neutrinos are coming. And with these 600 tons, they had about less than one event, and what they found was that only 1/3 of the predicted neutrinos were found, and that started the solar neutrino problem. So at that time, when this first problem was thought, there could have been many reasons. Like, one is that the experiment is wrong, because if you can see that this experiment had lot of steps, like to extract a handful of argon atoms from such a huge volume of the detector, and then there can be many steps where there can be some errors creeping in. Then some people said that, okay, the solar model calculations can be wrong, and one of the ideas were that maybe the solar electron neutrinos are getting converted to the muon or tau neutrinos, and the detector was sensitive only to the electron neutrino. So there were many new experiments which were done later to confirm this, and one of them was this predecessor of this super Kamiokande experiment, called the Kamiokande experiment, which is called the Kamioka nucleon decay. Actually, it was proposed, the Kamiokande experiment was proposed for something else, to see if proton can decay, which is proposed in some of the theories. But this detector could also detect the solar neutrinos by neutrino electron scattering. And these photomultiplier tubes, can record this event, and the neutrino electron scattering, one can reconstruct from which direction the neutrinos are coming, and also the energy. So from this direction reconstruction, so it was an experiment in real time, that an event is recorded, and as and when it is happening. It's not that after a while we are counting the events. And this Kamiokande experiment verified that the neutrinos are indeed coming from the sun. So there were many other experiments which confirmed this, but to get a final solution, we had to wait almost 30 years. So you can see that the first result came in 1968, and then the like when I did my PhD, that was about 95, 96, and even after that, around 2000, 2002, we had the results. So this remained unsolved, and at that time, after 30 years, some other experiments also confirmed that yes, that the solution is among the 3 solutions which were shown. That this is the solution, that the solar electron neutrinos are getting converted to muon tau neutrinos. So this is the phenomena of neutrino oscillation. So this is like in the sun we have one flavor of neutrino, and so when it propagates, it gets sort of mixed up, and we have all 3 flavors, and then at the detector again we can get these different flavors. So what started as a nu E getting converted to also having a component of nu mu and nu tau, and because the initial detectors were not sensitive to nu E, they could not detect it. But then there was one experiment called the Sudbury Neutrino Observatory experiment in Canada. That experiment could separately detect all 3 channels, and that's why they could show that there are indeed presence of nu mu and nu tau in the solar neutrino flux that is coming to the earth. So this is the phenomena of neutrino oscillation, where a neutrino of a particular flavor, after passing through some distance, get converted to some other flavor. Actually in the sun there is also the matter, so what takes place is not exactly the neutrino oscillation which takes place in vacuum, there is also matter plays some role in converting these neutrinos, the electron neutrinos, to some other flavor. So that is how this problem found a solution. Around the same time, there was also a problem that from the atmosphere we have the cosmic rays, and the cosmic rays were producing muon neutrinos and also the electron neutrinos. And the super Kamiokande detector found that the atmospheric muon neutrinos are coming less in number. First the Kamiokande detector found it, and then the super Kamiokande detector found that they oscillate to tau neutrinos. So the nu mu oscillate to nu tau. So in super Kamiokande the neutrinos, these are atmospheric neutrinos produced by cosmic rays. So they are coming from all direction. So some of the neutrinos are passing through less distance, and some of the neutrinos are passing through a large distance. And those neutrinos which are passing through the large distance can get converted to the other neutrinos. That is what super Kamiokande detector found. And because of this, this discovery was so important that 2015. So this discovery, super Kamiokande, came around 98, the atmospheric neutrino. So in 2015, the Nobel Prize in Neutrino Oscillation was given to Takaki Kajita of Super Kamiokande collaboration and Arthur MacDonald of the Sudbury Neutrino Observatory collaboration for the discovery of neutrino oscillation, which shows that neutrinos have mass. So Amol told you that I worked on neutrino oscillation. So what we worked on was, we worked on the this Sudbury Neutrino Observatory and Super Kamiokande data, and we tried to pinpoint what are the values of the parameters that are responsible for neutrino oscillation. And it turns out that this oscillation happens, so we quantify this by something. This can be explained if neutrinos have a mass. So there will be two different kind of states. So this is just simple quantum mechanics if you have already done it. And it is a simple quantum mechanics where we have the eigenstates as the mass states, which we call say nu1, nu2, and these flavor states are mixture of these mass states. So the parameters are the mass square difference, so that is the frequency of oscillation, and the mixing is by a mixing angle. So we tried to pinpoint what are the values of these mixing angles. The experimental collaboration of course provided some value, but there are different experiments, atmospheric and solar. There were also experiments using reactor and accelerators, and we tried to do a combined analysis of the solar and reactor data, and we tried to find what are the parameters which explain all the results. And so this is the kind of things that we did with these solar neutrino oscillations and atmospheric neutrino oscillations. So why it got Nobel Prize, why it is so important? Because as I said that such conversion requires neutrinos to have mass. So one has to go beyond what we already know. So what we already know is formulated in terms of something called standard model of particle physics, and in the standard model of particle physics neutrinos are massless. However, this neutrino oscillation experiments showed that neutrinos oscillate, so they must have mass. So that requires us to go beyond the standard model. And how neutrinos get mass is still an unresolved problem. There are many models, many parallel ideas. However, we exactly do not know what it is that is giving mass to the neutrinos. So apart from the sun and the atmosphere, earlier neutrinos were also observed from a supernova by the Kamiokande detector. I told about the Kamiokande detector. So the Kamiokande detector also observed neutrinos from an exploding star. So Amol is in fact an expert on working on the supernova neutrinos. But in 1987, these experiments like Kamiokande, there were 2 other experiments, they all observed some events. So this detector was not planned for a supernova neutrino detection, but it was like a serendipitous discovery. Because the supernova happened in the Large Magellanic Cloud in 1987 February, and these detectors saw few events. There were very few events, but they confirmed that, for the supernova theory says that only 1% of the energy is released in photons and 99% is released in neutrinos, and these few events confirmed this hypothesis. There were a lot of physics papers which came out only from these few events, and so if we have a galactic supernova, and then we can get immense information. So it's worth waiting for one, and there are many detectors planned which can do this. And because of this observation, in 2002, Nobel Prize was given in neutrino astronomy. So this is Ray Davis, who was the solar neutrino, and this is Koshiba for observing supernova neutrinos. And it was said that for pioneering contribution to astrophysics, in particular for the detection of cosmic neutrinos. So it was given the 2002. So it's very nice, if you read the Nobel lectures, then you can get a perspective from the people who have got these prizes, and they are normally written in a very lucid fashion. So I encourage you to read this not only in neutrino, but many other subjects, physics, many other areas you can read and form some perspective. So I have told you earlier, I have shown you the Crab Nebula through different telescopes. So here is a picture of sun through different messengers. So this is radio emission from, then this is infrared, UV, visible, X-ray. So you can see that different wavelengths can give us different pictures of the sun, and the neutrinos are coming from the core, and they are not interacting in the when they are propagating. So they can give us an idea about the core. So this is what I said, that they don't interact. So this is a picture of sun through different messengers. And this brings us to the topic of multi-messenger astronomy, which says that detecting astrophysical objects in more than one signal. So we can detect, like we have cosmic rays, then gamma rays. We have cosmic rays, then we can have gravitational waves, and we can have neutrinos also, gamma rays. So they can arrive, but neutrinos, there are 2 good things. One is that they can arrive directly from regions from where light cannot come, so they can come early. And also, they are not deflected in the magnetic field because they are not charged. That's why neutrinos can be an important, player in the multi-messenger astronomy. And but these neutrinos are very high energy. So when I talked about solar neutrinos, they are of MeV energy, which is like mega electron volt. And the atmospheric neutrinos are GeV energy, which is giga electron volt. But these neutrinos are very high energy. They can be 10 to the 15 GeV, 10 to the 16 GeV kind of. And then the idea, but when we go to this high energy, then the flux can be less. So the idea was how to detect these neutrinos. Then it was thought that the Super Kamiokande detector used water. So it was thought that if we go to South Pole, then we have ice, and we can have a large volume. So a kilometer cube detector was built, which is called the ice cube detector. So you can see this is the Eiffel Tower, and here this is a gigaton detector, and it is a cubic kilometer. And you can see that here, so this is how it is, like this is the ice top, and here we have the the detectors, and then we have these strings, and then we have these digital optical modules, and we have this so they put this, and then these are detecting the neutrinos, and then we can have high energy neutrino events. That was the idea. And one can go very deep in the core also. So this is sort of the ice cube detector in the South Pole, and sorry, this will not go. So this is how here also it is the Cherenkov process, like in the super Kamiokande. So when the charged neutrinos produces a charged particle, when they pass through it, they produces a Cherenkov radiation, and then the event is recorded. So this is how does ice cube work, that when a neutrino interacts with the ice, it creates other particles in this event. A muon, here they are showing that a muon was created and it traveled through the detector almost at the speed of light, and different these detectors are hit, and they show that when they are coming. So color indicates arrival time, red is first and green is last. So that's how an event is triggered. And so the ice cube observed, so ice cube observed the highest energy neutrinos from distant astrophysical object first time in 2003. So they named it in terms of cartoon characters Bart and Ernie, and then this Big Bart, there was another event, so 3 events. So that was the first time that a very high energy event was recorded. And then the question, so one of the question was that from where these very high energy neutrino events are coming. For the sun and the atmospheric neutrinos, we know that they are coming from the solar neutrinos, and atmospheric that they are coming from the sun, they are coming from the cosmic rays. But what is the source? What is the source of the high energy astrophysical neutrinos? That was not known. And then in 2007, a correlation was found between a high energy neutrino and a flaring blazar. So blazars are sources which can produce gamma rays, and there are experiments like Fermi and Magic who recorded these events, and there was a correlation found, and that was the first ever identification of a likely source of high energy neutrinos. So this initiated the multi-messenger astronomy with neutrinos, because we found a correlation between a neutrino event and a blazar, so that may be the source of this. And so apart from ice, we can also have a large volume of water in the sea, and in 1960 A.M.A. Markov proposed that maybe we propose setting up apparatus in an underground lake or deep in the ocean in order to separate charged particle directions by Cherenkov radiation. So it is the Cherenkov radiation. When a charged particle is passing through a medium, it can exceed a speed of light and it can emit Cherenkov radiation, and that's what was employed in Super Kamiokande as the basic principle in ice cube, as well as for the undersea detector. So this is the cartoon which came in New York Times, that this is a normal astronomer who are going up in the hill to observe, and here a neutrino astronomer who is going down in the sea, in the mine, they are going in the South Pole and putting under in the ice, digging deep in the ice, like that. So there are this is the KM3 net at the Mediterranean Sea. So this is one is oscillation research with cosmic in the abyss. This is called ORCA, and another is astroparticle research with cosmics in the abyss called ARCA. So this is to measure the atmospheric neutrinos. So this is, as I said, giga electron volt energy, and this is location in France, somewhere in the Mediterranean, and this is about 7 megaton detector. And another is the at near Sicily, Italy. This is astrophysical neutrinos, so very high energy, 10 to the 15 GeV, and they have this 500 megaton to 500 megaton detector. So these are the 2 detectors that were planned in the Mediterranean. And so this is the KM3 net deep water telescope, detects the flashes of Cherenkov light from neutrino interactions. So they were saying that how do you know they are just not the fish? So this is an important point, and they have to go to a biologically quiet area, not very active, but of course Cherenkov radiation is only emitted when things exceed the local speed of light, so it cannot be produced by the undersea life. And in fact, this year in February, this KM3 net collaboration has reported detecting the highest energy neutrino, and this is deposited in neutrino energy is like 120 PeV, and so that can come from a muon of 220 PeV. So this is the this is the size of the detector. You can see comparing with the Eiffel Tower, and they had this Cherenkov radiation. These detectors were triggered, and they have recorded the event. Now the thing is that there are many questions which this single event has generated, that whether it is of astrophysical origin, whether it can be coming from the galaxy, is it coming from cosmic rays, and also why Ice Cube, which has been observing these high energy events, have not seen such an event, such an high energy event. So this result came in the February 25, and this is really a very active area now. So that brings me to the end of my talk. And what is the take-home message is neutrinos are all around us, and they interact very weakly, so we need huge detectors, and they have some weird properties that they change into another type, and they oscillate, and that gives us many interesting clues about the neutrinos, but there are still many unknown questions, and so this is still a very, very open and interesting and active field. And with this, I also wanted to mention a little bit about Leelavati's daughter and my journey, because I think that is one of the ideas to to tell people that what is it and how we are here. So in Leelavati's daughter, actually Rohini, this was a biographical essay of many women scientists, and I think there were many women who have faced some problem in their life, in the sense that one of the problems, like I named my article as Tale of Two Lives, and by that I mean that I had a conflict between my family life and my career, because I was not getting a job in the place. So like now I am in PRL, my husband was in PRL, but PRL didn't give me a job. So I had two options: either I have to leave research, or I have to continue, but I have to stay away from my husband. But I had a small daughter, which made it very difficult. Small means she was just 2 years old, and it made it all the more very difficult. And so when Rohini asked me, I think Rohini, at that time they chose people who had faced, because these kind of problems, even now people are facing, but they were really, really very severe. And so that time she asked me, and I was really busy in managing my career, my daughter, and I was not giving the article. And Rohini once scolded me. She said, "Subhabhuti, do you think you are busier than me?" And that made me thinking that, even though I am busy, I cannot be busier than Rohini. So that motivated me to write the article. And if I had not, this made me a part of a history, which I had really missed. So I'm really thankful to Rohini for that. So I started with that, A Tale of Two Lives, and it was a struggle for survival. I didn't know if I will be in physics or I will not be in physics. It was a question mark. You go and people will ask you, okay, like, people will first say, PRL is not giving husband and wife, you will not get job. I don't even know if I am suitable for a job. I have not even proved myself to that, whether I am capable enough to get a job. It was just after my PhD. But still, I continued, and then last year, INSA brought out this book, like Archana Sharma, she is in CERN, and K.S. Harshita, she is a science writer, and that Women Shaping Scientific Frontiers. And in that, this title was chosen by me, this title was chosen by them, and it says Lifelong Exploration of Science. And I'm really lucky, and also I was very determined that, from this struggle for survival, I came to a stage where I could explore what I like lifelong. So that's the kind of transition, and I thought it's nice to talk about it. And there are many, many women who are doing science, who are excelling in science. So, faces of Indian science, we should remember that, there are so many women who are doing so good in science, and the situation is improving a lot, much better than it was when we were doing. And so the question is that who is a scientist who can, observes and wonders, shares their ideas and discovers, listens to the ideas of others, explores the world around them, asks questions, uses tools to save problem, conducts experiments. So a scientist can be anyone, like it is someone like you, someone like us. And in this context, I wanted to share a quote which Rohini said, which is very apt. And what she said was, it is more than our gender, it's the science that we do. And that is most important. Thank you.
We can have questions to Shivavati ma'am.
You can ask anything. Yeah.
Thank you, ma'am. Ma'am, I have this doubt that already the neutrinos are very, like they don't interact much, very low energy. But how do we know?
No, low energy, it can be high energy
okay,
also.
high energy too, but they don't interact much.
They are weak interaction.
Weak interaction, okay. So first, like we know that, okay, there are electron neutrinos, they interact at first, and then how we get to know that, okay, then they change their flavor, because after one interaction, however it is very, very less we can find out, okay, they are interacting. Like how we...
So there is it is not that they are non-interacting.
Yeah, they interact.
There is an interaction which is a weak interaction. Its strength is less, for instance, as compared to the electromagnetic interaction of the photon.
Yes.
Now, the neutrinos, there are two things. One is the neutrinos propagate. So there is not a single, there are, so for instance, from the sun, we have the electron neutrino coming out of the sun. So it is produced as electron neutrino. Then when it is propagating, as a different state, which is the eigenstate, mass eigenstate we call it. So I don't know, have you done quantum mechanics? So you've done particle in a box, right? Supposing you do your particle in a box eigenstates, but sometimes you have this question, no, that supposing I have a mixed state and we find that, they are mixture of the different eigenstates. So it is like that. I have a neutrino which is produced. When it is produced, it is either an electron flavor or a muon flavor or a tau flavor. Then from the sun, when it is coming out, it will be a mixture of nu1, nu2 and nu3. Then it is coming to the detector. There it is interacting with the detector. The interaction strength is very low, so we have very few events, but there will be events.
Yes, ma'am. Like after the one interaction, they will lose energy, right? Like while interacting, they lose energy, and that's how we get to know that, okay, neutrino is coming.
When after they interact, they get converted to a different particle. So if I have a nu mu, it will produce a muon, but I have a flux.
Okay.
So what I am detecting is not the neutrino. I am detecting the muon. So that is the thing. If I have an electron neutrino, then what I am detecting is the electron.
Yeah.
Charged lepton. That's what we are detecting.
Okay, ma'am. Like I'm a bit confused with how change in the flavor, that like how we get to know that, because after one interaction we go, okay, it's a,
this is like it is not the interaction which is changing. It's a quantum mechanical interference type of a thing. So I didn't show the maths here. So you can do the maths, like I write the nu e as a superposition of nu1 plus nu2. Then I write a nu mu as a superposition of nu1 and nu2, two different superposition states. Now we have to see how they evolve with time. So we will do the time evolution, then you just calculate your quantum mechanical probability. What is the probability of finding the initial electron neutrino as an electron neutrino? So that probability will give you that how much has gone to the muon. Normally we are in the regime where my Hamiltonian is Hermitian and I have the probability conserved. So if I have two flavors, then if so many neutrinos have gone to, if the probability is 0.5, then 0.5 will remain as electron neutrino, 0.5 will go to the muon neutrino.
Ma'am, I wanted to ask, is it possible to build a neutrino detector in the space, like to avoid the all the neutrinos in the atmospheric that
See, in
we...
the space, the main problem is that, you have to have small volume.
Okay.
And neutrino detectors typically need large volume. But there are some NASA ideas that, where they are trying to get close to the sun to detect the neutrinos.
Thank you.
There were, when also we were doing this starting research, that time there are this accelerator, I didn't talk about them, accelerator neutrinos, which are man-made. I talked about solar neutrinos which are coming in nature. Accelerator neutrinos, like in Fermilab, for instance, there will be some neutrino beam which will be detected at some distance. These are called long baseline. So they are going about, say, 1,000 kilometers. So when I started research, that time there was some proposal, Fermilab to moon. So maybe one day, you had that Fermilab to moon proposal at your time, it was there? Never. But these kind of ideas are there, we should think.
Good afternoon, ma'am. Ma'am, how do we correlate Cherenkov radiation with neutrino detection?
Because neutrinos are producing charged lepton. When a charged particle is going through a medium, if its speed is more than the speed of light, then it can emit Cherenkov radiation. So you can calculate in water the cone Cherenkov angle, and then you can calculate the speed, whatever you have done, your simple Cherenkov in electromagnetic, and then you can see that it can emit. So water, that it can emit.
Thank you.
Ma'am, thank you for the lecture. I wanted to ask one thing from one of your slides where it was told that we can detect the neutrinos before the light. So does it mean that it travels faster than the light? Or
No.
could you explain that?
It doesn't travel faster than light, although there was some claim at some point of time, so I don't know, internet you may find, but that is proved wrong. It travels in the speed of light, but the light is interacting.
Okay.
So that's how we call light is getting trapped. So supposing it's coming from the sun, light is interacting with the solar matter, so that is causing it a delay. But the neutrino is very weakly interacting, much weaker. So then it will coming faster than.
So if it's
before the light, that doesn't mean it's traveling faster than light.
So like it is formed together, but light interacts, so it gets delayed. But
It is the same PP chain like the solar sun,
Okay.
which is producing heat and light. That is also producing the neutrino. But then neutrino is not interacting. But when the photon is going through that, then it is interacting. So the neutrino is coming earlier.
Okay.
Because of it is weakly interacting. So because it is weakly interacting, it's difficult to detect them. But because it is weakly interacting, it can give us information from an earlier time.
Okay. Thank you, ma'am.
Thank you, ma'am, for such a wonderful lecture. Ma'am, I have two questions. May I ask some short questions?
Sure.
Ma'am, first of all, am I correct to assume that the directionality of the detection, basically where the source is there in this space, is it inferred from the arrival times of the individual detectors?
So it is if you have a Cherenkov cone, so you can reconstruct from which direction they are coming. Okay. So it's from that cone direction you can reconstruct that direction.
Okay, ma'am.
And
Thank
the
you, ma'am.
time information is there.
Yes, ma'am.
So that cone, so this ice cube plots I showed, different detectors are getting hit at different times. Yes. But the direction should be, the reconstruction should be like point towards some direction up to its resolution. For instance, for the sun, I know that, then Super Kamiokande or Kamiokande could prove that it is coming from the solar direction up to some detector resolution.
Yes. Thank you, ma'am. And my second question was a bit weird one because, like we mentioned that the neutrinos that we detected traveled almost close to the speed of light. But I mean, to measure such velocities, don't we have to have the detectors, clocks synchronized perfectly? Like in that case, relativistic effect may come to the picture, and like the concept of simultaneity may come to the picture.
When we are having the oscillation experiments, then we can calculate the oscillation probability, And we can do it in terms of like we are assuming that the neutrinos are relativistic. So that
maybe I can
you
comment.
can can
So
comment.
the experiment which did this with the largest precision actually was the experiment which sent a beam from CERN to a lab in Gran Sasso in Italy. Okay. And
Yeah.
there they used to send neutrinos in bunches whose width was, I think, 5 picoseconds. Okay. And they would detect that bunch at Gran Sasso.
Yeah,
The distance between labs was very precisely known. It was being tracked by using GPS just to ensure that things are not changing. And therefore, they could determine the time taken by neutrinos to reach from CERN to Gran Sasso, with an accuracy of about 10 nanoseconds. Now, 10 nanosecond is the distance taken by light to go from Shubhabati to me. Okay? So, which means that the distance between CERN and Gran Sasso, which is about 800 kilometers, was measured to an accuracy of this much. And that allows you to measure the speed of neutrinos to a higher accuracy.
Okay, sir. Thank you very much, sir.
But,
Thank you, ma'am.
means what I was trying to say is before all that was measured, this was measured and there was a confusion that this experiment measured something that neutrino is traveling at a speed greater than light. But in our calculation also, when we do that the neutrino is traveling at a speed is relativistic, that goes in. When I am doing the oscillation calculation,
Okay,
there
ma'am.
also it goes in.
Okay, thank you, ma'am.
But there, that's not measuring the,
Yes.
that is measured by that experiment which Amol said.
Thank you, ma'am.
Ma'am, in one of your slides, you mentioned the radiochemical experiment that why do we use only cleaning fluid like chlorine and argon?
See, you have to use some reaction, where, so this was like, you have to see many things. Like there was also another experiment which used gallium in different form. There were 2 different gallium experiments which used gallium like a radiochemical. So chlorine was, there are many things. You see the availability, the cost, then some reaction. So you have to have a Q value of the reaction. So here they were trying to observe the 8 boron neutrinos. So there are, when I am saying the solar neutrinos, then it's like the different energies. So there is a pp chain and there are different energies of neutrinos. Depending on, there is a low energy neutrino. So the main neutrinos from sun are the pp neutrinos, which have the low energy but they have maximum flux. So this is up to about 0.42 MeV. And what they were doing was the chlorine, high energy 8 boron, that is 5 MeV. So there are these various considerations which goes in, which they will do, but there was also another 2 radiochemical experiments later using gallium.
Thank you. That you are saying that neutrino carries information about the star. So how we extract information about stars from neutrino when it doesn't have charge or mass?
So, it's a very good question because I didn't talked about it, but I will be happy to talk about it. I will tell you how this experiment which established neutrino oscillation by detecting the nu e, nu mu, nu tau, all the 3 flavors, also tested the solar model. Because this experiment, as I said, there are different neutrinos. This experiment was sensitive to the 8 boron neutrinos. Now, when earlier neutrino experiments were saying they are getting less neutrinos, they were having only nu e. Now, if I have nu e plus nu mu plus nu tau, then it should match the flux that is calculated. So, this experiment, which is the Sudbury experiment for which MacDonald got the Nobel Prize, it measured that when it detects all 3 flavors, nu e, nu mu, nu tau, then the total flux matches the 8 boron flux that was calculated by the solar model. So that's how it could test that, by checking how many neutrinos are coming. Like for the supernova, for instance, that, when the neutrinos are coming, then first of all the supernova model says that there will be so many neutrinos coming, and then neutrinos coming out is a proof of that, hypothesis that, it's coming. So that's how.
And then,
Maybe,
ma'am, in
Maybe I
Amol
just
can
add
add
to this
something.
slightly, which I think you mentioned, but very quickly. So the probability of neutrino oscillations depends on the density of matter that neutrinos pass
Yeah.
through. So if you measure the amount of neutrino oscillation, then you know about the density of matter that they pass through,
Yeah.
which is like telling you something about the internal structure of the star. So that's
That
something.
is also there.
In fact, that was an important part of your work from 2000.
Yeah.
And my ma'am, second question is, in the first time we detected the neutrino is in Japan, then we used 50 kiloton water, then we used ice, then we wanted to build a detector under the sea level. Why water is so important when we are detecting?
It's
a neutrino?
available, no, and you need large volume. So the Sudbury Neutrino Observatory used heavy water. But water is like, this is a natural availability, and water has the required Cherenkov cone to have the Cherenkov radiation.
Thank you.
The cost is very important in these also, and the availability of the detector material. In India, we were trying to build an iron detector because iron, it is magnetized. But then it's very difficult to have such huge iron detectors.
But ma'am, if we will use iron, but the neutrino doesn't have any charge, then how we will use
Because neutrino is producing a charged lepton in the detector. So that can help. That is one thing very important we have to remember, that the neutrino is producing a lepton, charged lepton, and that's how we are detecting the neutrino.
You mentioned in your talk about the need to go underground, under the sea, and so on. Do you want to say something more about why you should go underground?
Means I told that because we should not have. So, for instance, there are cosmic rays coming. So, in the atmospheric neutrinos, we are measuring the muons, but the cosmic rays can also give me muons. So, we should be sure that these are not the muons coming from directly, but there can be other sources of muons also, radioactivity, etc. So there is something called a background. So we have to have a background, good background suppression. So background means that this event is coming from the source that I am observing, it's not coming from any other source. So that's why one has to go underground to have a pure atmosphere, pure surrounding, so that you are not confused by some other source as neutrinos. So that is the main reason for going underground, so that we have a good background resolution.
So while people are thinking of more questions, I know that Arnab sir sitting here could have become a neutrino physicist but did not. Okay, so I'll ask him why he did not become a neutrino physicist.
I almost did. So when I went for a PhD, the way it happens there is all the groups are trying to attract students, come and join our lab. And I was at the University of Wisconsin, which was the lead university for what was the predecessor of IceCube called Amanda.
IceCube is even if they are the
Yeah, but IceCube initially a smaller version was called Amanda,
yeah.
Antarctic Muon and Neutrino Detector Array, okay, at the South Pole. So now they were very good. They had the best cookies, right? All these labs used to organize talks and there'll be cookies before the talk and you went for the cookies. Now, and there were some other, they was like, the experiment is fantastic. Believe me, this IceCube and whatever, Amanda, the technological challenge of being able to drill into the ice cap, put your detectors inside there, get the signal out, process it. It's got, amazing experimental thing. Very nice. And then the people who came, Wisconsin is in the Midwest where it is miserably cold. It was minus 40 in winters. And they needed graduate students to go and take care of the detectors in the Antarctic during the Antarctic winter, because the scientists would all come back. So students would go and take care of it. And after they went, when they came back, they used to all roam around in shorts in winter when it was minus 40, because they were used to really cold places. So, even that is fine. Good. Looks like these guys look like very cool. So then I went and signed up for it. So the first thing they gave me was a form, which says, go and remove your wisdom teeth. And I said, what? What's this got to do with thing? So apparently under US law, a dentist is not allowed to remove wisdom teeth. A wisdom teeth can be removed only by a maxillofacial surgeon. Now there is only one medical base at that time, at least in Antarctica, where there was a dentist. So if you had some other teeth, something go wrong, they could do something to you. But if your wisdom teeth, something happened, they can't do anything to you. And for 6 months, they cannot send anybody to get you out. Right? So the only thing you can do is you have to get all your 4 wisdom teeth removed before you go to Amanda. And that was the last thing, and I never went back there. So I decided I'd rather keep my teeth and do something else. But it was probably, of all the experiments we were exposed to over there, it was certainly probably technologically at that time the most advanced experiment I had seen. Maybe CERN and all were something, but here it was, because people used to fabricate. I mean, there was chains of things with little spherical
optical modules.
Little spherical modules which used to host the thing, and they would be on a chain. They use hot water to drill, and they put it in, and the water refreezes, finishing because it's got to be one solid piece. And what is amazing is, remember, if you're drilling into the ice, it's not a uniform block of ice. That ice holds a record of everything that has happened on this planet in the years that that ice cap has formed, right? So when a signal has to go down, they have to monitor what was volcanic activity in the 1800s, because those layers of ice have a little bit more dust than other layers of ice, so the beam will be slightly slowed down there. They used to take into account all these things. And this is by far, in terms of, we think, what are the possible errors in this experiment, things which they ask you in physics. I mean, these guys, when they spoke about the way they designed the experiment, any young physicist would think of like, wow, I want to work on that. Except the teeth part. So, yes, but I draw the line at some point. Otherwise, I mean, all these people need to work on neutrinos. No? If I also went there, come on.
No, I used to think that, I will be very happy if I can go to South Pole, but I didn't know this part, huh? So, now you cannot go. Sanjeev told me that you have high pressure, you cannot go anymore. So I lost the chance.
So, yeah, thanks for the nice talk. So, as far as I understand, up to 90% confidence interval, we know mass is less than 1 electron volt or something, 0.8.
See, it's not, what we know is from oscillation experiment is the mass squared difference. Because it's like the oscillation depends on the mass squared difference between the propagating states. So the flavor states, the nu e, nu mu, they are propagating as the mass states nu1, nu2, and oscillation experiment measured the mass squared difference. And the solar neutrino data which we fitted says the mass squared difference is 10 to the minus 5 eV square. And the atmospheric neutrino data says the mass squared difference is 10 to the minus 3 eV square. So we have 2 mass squared difference which you can correlate with 2 oscillation frequencies in the system. But there are beta decay, you can estimate some mass. That's some 2.2 electron volt less than right, but that's not exact. Recently how much? It has reduced, okay. The new result. So that is not though the mass, it is a combination of we call it some effective mass, a combination of mass and the mixing angles. But from cosmology also, we know that the sum of the neutrino masses should be less than sum of the 3 neutrino masses should be less than 1 electron volt. So they are very tiny. The bottom line is the neutrino mass, even if there, it's very small. That the sum of all 3 neutrino masses should be less than 1 electron volt. In fact, now the data says it should be, depending on which data use, can be less than 0.5 electron volt also.
Yeah, but okay. So Because that's the case, and I see in a lot of talks where people talk about all sky maps. So we have optical, radio, gamma, all sky map, and people then say, can we have neutrino map so that we can look much more farther into the universe because of. But given this sum of mass limitations, are we also limited by how much sky we can map? I think
I don't think there was this Milky Way map, no, which IceCube did. They have found the neutrino map of the Milky Way using the AI. Here the problem is the very weakly interacting. So, the event is very less. So if you have very less events, then from that drawing an inference is a problem. But recently from this IceCube experiment, they had used some AI tools and they have found in the Milky Way that neutrino map. So I don't think the mass is a problem there.
So there are maps of high energy neutrinos, just that they are not as well filled as the maps of electromagnetic waves because events are small. So get old and you will see meter maps.
No, this is just a comment, but a very nice talk. This is just a comment to her question about how do you know the structure of the star if the neutrinos. And I know, I don't stand a chance here because I'm surrounded by particle physicists, Rohini's daughters and son. But astrophysicists, so this is one piece in the puzzle of how neutrinos are one piece in the puzzle. The main clue of the internal structure of stars don't come from neutrinos, but rather stellar oscillations, so solar oscillations. So the branch of that for the sun is called helioseismology. So in the 90s, when helioseismology was at its golden years, I would say mid-90s, so this was a big tussle going on because solar physicists from helioseismology, which can pin down the model of the sun extremely precisely, were absolutely almost sure of the solar model. But particle physicists argued that no, there's something wrong with the solar model, you have to fix the solar model, and the astrophysicists were saying, no, you have to fix your particle physics because this thing doesn't match. And then when finally the puzzle was solved, so there's a great rejoicing among astrophysicists that there's nothing wrong with the solar model, it's absolutely right, and it's just the particle physics, the neutrino oscillations thing was what was missing. So when Amol says that only about 10 years ago, we know how the sun, why the sun shines, that's not quite correct. We know it for 30 years. But the particle physicists needed some convincing, yes.
Actually, Anish reminded, Anish, I worked on a heliosismological model and the solar, trying to bridge the two. And I worked with Chitre and Antia. So they have this heliosismological model and they have the flux. And what we tried to do is we take not the Buchholz flux, but we take the flux from this heliosismology and we fit our oscillation data and we see that what are the parameters that we get and those kind of things that we also did, that what does it say. And yeah, it didn't say. It also pointed out that the particle physics, some particle physics correction has to be there.
Any more questions? Okay, if not, let's thank Shubhabati again. You can still find her outside when we are having our tea, coffee. Is it here or? Here, okay.